So the next item here I want to cover is called rebar spacing. The rebar spacing, it's the clear spacing, and I was very specific on my slide. I put this in red and in capital letters, you guys understand, because later in my course, not now, you will hear about other spacing, but those spacing are center line to center line. But here, since we are concerned about that we have enough gap between the rebar that allows the concrete to flow and wrap around the rebar, then this is the clear spacing. Now, it comes from the code, and I will give you here the reference. So table 2.6 on CSA 823.3-14, you will find this picture here. And so this picture, it shows you the spacing between the rebar and how to find the spacing between the rebar, the minimum amount. So just let me introduce for you the definition. So D sub B is the reinforcing bar diameter. Reinforcing bar diameter, okay? And something also you learned about it last year is something called nominal maximum aggregate size. You guys know that our aggregate that we use for concrete, it varies, and it's characterized by something called a nominal maximum size, which kind of a dominating size of your aggregate. And this number, it can be 10 millimeter, it can be 20 millimeter, and it can be 40. I think in the next one is 28 millimeter, and the last one is 40 millimeter. And I haven't seen any aggregate more than 40 millimeter. Also need just kind of refresh your memory that guys, ultimately you would like to use a bigger aggregate, because bigger aggregate, it has less surface area, and it will need less cement to cover the surface area. But it depends on the thickness of your structural element. Sometimes it's very thin and slim, so we cannot use 40 millimeter. And sometimes I'm pouring a mass concrete, like a big amount, and that's where you can use the big aggregate. Okay, I'll tell you something. Please take a note with that, and probably I will add this to my slide sometime. I will take a note. The aggregate size, the most common one is 20 millimeter. That's the most common. So in most of your work, you will see a 20 millimeter, which is 3/4 inch. That's the most. But sometimes for a slim member, like member with smaller thicknesses, like tubing, concrete tubing, and slab, like your basement slab, where the thickness is only 4 inches. And in this case, what we do is we use a small aggregate, which is 10 millimeter. Okay, so I think in my class here, we will always use 20 millimeter, like 3/4 inch aggregate. Okay. Anyway, next. How do I find the spacing or the minimum spacing between the rebar? And I'm clear also, I said in all directions. So you can see in my cross section, there is a spacing between the bars in one layer or one row, and also there is a spacing between rebar vertically here. So when we say the spacing, it means all around your rebar. How we do that? So the code says it has to be larger or equal 1, 2, 3 numbers. 1, 2, 3 numbers. The first number you want to estimate is 1.4 multiplied by the size of your bar. The size of your bar. And the next number is 1.4 multiplied by A maximum, which is the aggregate size. And then 30 millimeters. So what you have to do is you need to simply estimate the 3 numbers and simply pick the maximum among them, and then this will be your minimum clear spacing between your rebar. Something also I want to mention on the side, what if your beam has different sizes of bars? Like let's say on this lower layer, I have a 25 m, and on the top layer, I have 20 m. In this case, it looks like I have to go with the maximum bar diameter. So you can think about this bar diameter is the maximum bar diameter if there is 2 bar sizes. But if there is only one, that's great. So we use it. Okay. So right away, I have here a numerical example for you. which is, I give you here some numbers here. If the D sub B, which is bar diameter, is 25 millimeter, it means 25 M. And the E sub maximum is equal to 20 millimeter, which is the most common aggregate size. How do I find what is the minimum spacing? Then S is equal to maximum of 1.4 times bar diameter, or 1.4 times aggregate size, or 30 millimeter. And guess what? This one will be the maximum, is going to be a 35 millimeter. Okay, 35 millimeter. Okay, now, so which means when I place my rebar in a beam, I have to make sure and maintain a minimum of 35 millimeter. Otherwise, I will be in trouble. Okay, guys, this equation here, or this math here, or this spacing here, will really dictate the width of your beam. And sometimes your width of your beam will dictate the layout of your rebar. Because think about it, huh? I think this is a good picture to understand this concept. From each side, I need a spacing, a cover, a concrete cover. And then I have a stirrup. Then I have a bar. And I have two bars, 3 and 4. Looks like I have to maintain a minimum value for the spacing between the rebar. And if I do not enough much space to maintain the spacing, then looks like I have to place my rebar on another layer. And that's where this S will play. One more time, the spacing between the rebar, the minimum as per the code, will dictate the layout of your rebar. If you have enough spacing, then we place them in one layer. If we have not enough spacing, we simply add them in a different layer, in a second layer. Okay? Guys, also, I'm not sure if you already have that much experience to be able to see bundles. Like sometimes we do rebar bundle. When I say rebar bundle, it means we don't maintain the S, we just bundle them so they are touching each other. Okay? So it's not very common. We use it only when there is a really so much reinforcement, like a forest of reinforcement in your beam, and this is not the norm for building, like a condo building, or like a even high-rise building in beams, not like that. Okay, but for example, if you think about girder, like a bridge girder, where the span is 40 or 50 meter, and so in this case we need lots of rebar, and the spacing is not sufficient. So what we do is we simply group them, we bundle them. But I will mention something which will be kind of advanced for you guys. When we bundle the rebar, it means we have to, they will not be that efficient, because concrete is not going to wrap around the entire perimeter or the surface of your rebar. That's why in our design, we have to reduce the area of those bundles. Anyway, this advanced, it's outside my course scope, and we will never do it. We will always maintain a clear spacing between the rebar. That's it. Okay. Now, guys, there's something called, I call it centroid calculation. As you can see here, when I talked about the beam, when we talked about effective depth, effective depth looks like I'm measuring the D from the top of the slab. So here we go. So here where I start from the D, top of the slab, top of the beam, and then I go all the way to the centroid, or the center of the gravity of my rebar. And that's why I felt that it's very important for you guys to remind you very quick, on a very quick basis, on how do we find the centroid of the rebar. Here we go. So guys, I gave you here 3 different examples, not only 1, 3, because simply our rebar can be one of the following cases. Number one, if my rebar is on one layer, and all of them, they are of the same size and the same, same size. So you guys know, if I ask you, where is the centroid of this 315M? Anybody to tell me where is the centroid of those 315M? Show your hands, please. Okay, Domenico, go ahead.
Are you talking about all 3 together?
Yes.
Well, I'm gonna assume right in the middle of the middle one.
Yes, it is. Thank you, sir. Okay, thank you. Domenico, a couple of marks for you. Okay, so yes, true. The centroid, I'm going to mark you the centroid. So the centroid is here. This is the centroid of the group of the rebar. Okay, so you can see here, since the H is given, like when we design, we know the H is 800 millimeters. And but in our calculations, we will need the D. We will need to find the effective depth of your beam, because this is really what matters. Like the H, we don't care the H. In our calculation, as you will see, and hopefully this will make sense for you, it is the D. The secret is the D. How do I find the D from the H? Please look at this one, please. So you can see there is a D goes from the top of the slab to the centroid, and there is a D prime which goes from the centroid to the bottom of your beam. So really the secret is simply finding the D prime, and once you find the D prime, then here we go, H minus D prime will give you the D. So let's do that. So there are some very simple cases, which I guess all of you will know how to solve this simple problem, because we have one layer of rebar and all of them are of the same size. Then in this case, we know where is the centroid. It is where I pointed with my arrow, Now, very simple how to find the D prime. I'm going to zoom into the bottom and you can see. So from the bottom, we go with the cover. So the cover is here from the blue to the stirrup. And then we have the diameter of the stirrup. And then finally, we have half bar diameter. Look at my math. So one more time, concrete cover is 40. 10 millimeter for the stirrup, which is the norm, the common one. And then if I have 25 M bars, then I use 25 divided by 2. Please don't use 25.2 because that's in the code. We agree that we always use the bar number, not the nominal dimension for your rebar. So what you get here is a 62.5 millimeter. So basically, the distance from this point here to the blue is simply 62.5, and the depth is equal to the effective depth is equal to 800, which is H minus 62.5, and then you get this number 737.5. Since we're talking about the beams, also I'm going to train you right now on the same topic on how to find the reinforcement ratio. Reinforcement ratio is the ratio between the amount of steel, and I'm very specific, it's only the main reinforcement. So because I have 325M, please take a moment and go to the table. I'll go to the table very quickly here. So I'm referring guys to this table. So this table, anytime you wonder what is the area of 25, you go to this table. So 25M, each has a 500 millimeter square. Okay, now since we know that each one has 500, it means the 3 will have a 1500. Here we go. So 3 times 500, this is the area of the steel. You divide by the width of the beam, you divide by the effective depth of the beam, and you get 0.0067. And we always express the reinforcement ratio in percentage, and this number in percentage is 0.7%. Okay. Guys, any questions so far before I continue? Do you have any questions so far? Again, this should come from your strength of material, and this one is easy. This one is easy. Now, if you don't have any question, I will just proceed to the next example, which is a little bit more complicated. So the next example is, I have here a beam, and this beam, I placed my rebar in 2 layers because simply there is not enough space for 4 bars in 1 layer. Okay, there is not enough space for 4 bars in 1 layer, and that's why I placed them on 2 layers, because the beam width is 300 and it doesn't allow, and we will do that later on, not today, but later on. We'll teach you how to check whether 300 is enough to include the 4 bars, 25M, with all the proper cover and spacing. It doesn't, okay? And because it doesn't, that's why I put them in 2 layers. Now you can see I maintain the spacing, and again, if you go back to the example that I mentioned a minute ago, we are able to find a spacing minimum 35 millimeters. So the spacing here in all directions must maintain 35 millimeter. So now let me ask you the question one more time. With this group of rebar, where is the centroid of this group of rebar? Show your hands, Mahdi.
The center between all 4 points, all 4 rebars.
So I'm gonna give you options and tell me yes or no, please. So
Okay.
is my centroid is here?
No.
My centroid is here?
No.
My centroid is here halfway?
Yes.
Perfect. Thank you so much. That's true. And that's why, look at this, please. If you look at the anatomy, you will see the D prime here. Look at the D prime, which is the secret. So the D prime will include the cover from the blue to the stirrup, and then will include the stirrup, and will also include the full diameter of the rebar. And then finally sits in the middle. So we have to add half of the 35 millimeter, which is half of the spacing. Let's do that. Here we go. So we have D prime equal 40 cover, 10 millimeter stirrup, 1 bar diameter, and then half of the spacing, 92.5. And I'm asking you, why 35? Please go back 2 slides ago and you will find the answer. Why 35? And the assumption here is the aggregate size is 20 millimeter. Now, next is, once we find the D prime, we're able to find the D, very simple, same 800 minus 92.5 over there, you get 707.5. Then finally, if we wish to find the reinforcement ratio, it's very simple. You divide by area of steel, and since we have 4 bars, so here is the 4, and since every one is 25 m, which is every 25 m is 500 square millimeter. I bet you by the end of my course, you will memorize the cross-section area of a 10 m, 15 m, 20 m, and 25. Not more than that. That's what you need. Anyway, so it's 0.0094, and as I said, we always express in a percentage. So this is going to be 0.9%. Let's move on to the last and the most difficult one. The last and the most difficult one, and this one probably you have to remember the strength of material. So in this case, it is asymmetric. It means different size and or number in every layer. Look at this, please, and which is both of them. So that's and. So in the first layer, we have 325 m. In the second layer, we have only 2, which means layer 1, layer 2, they are different in size and also different in number. However, it is and or. It means if they are different in size, you apply the same business. If they are different in number, you apply the same business, or even both. If both, like number and size, you apply the same business. Okay? And that's why I said here and or. Okay? And or. Okay? So in this case, you're finding the centroid is not as easy. And guys, the centroid here, I'm going to ask you, the centroid here, is it the same as last question? Please show your hands. Oh, looks like nobody's following. That's very disappointing. Okay, Brody, go ahead.
Sorry, can you? Okay. The centroid, I'd say it's probably a little bit closer to the bottom 3, still in the center.
Okay, you know what? I will give you not only 2 marks, I'll give you 4 marks, and I'll tell you why. Okay? So the answer is my question was not that. My question, as I said, was it the same as last question where the centroid is in the middle? Okay, so the answer is no. I guess that's implicitly what it is no. And the centroid will come really closer to the 3 because the time when we have like more area, simply the more area will attract the centroid to the more area. So we have a more area on the lower layer, and that's why the centroid will move closer to the lower area. Sorry, the lower layer. Now, how we do it is we simply use this math, okay? Okay, so guys, I know that what I'm writing on my screen is not really friendly, but this is how mathematicians, they write their equation because they want to scare us. They want to scare us, but we're not scared. Where is Hamid? Where is Hamid? Do we have Hamid? No? Okay, anyway, so listen, again, a mathematician, they write things in kind of a complicated, but let me read it for you and then I'll explain that this is super easy. So to find the D prime, which simply finds for you where is the CG, you have to do the summation of the first moment of area, So you get the area, you multiply by the where is the centroid of every area, and you keep doing this from I equal to 1 to n, and then finally you divide by the sum of your areas. Okay, let's do it. So guys, when you apply this equation, you can simply think of I, it can go from 1 to 5. 1 to 5. Why 1 to 5? Because simply 1, 2, 3, 4, and 5. Okay, which you will get the same results if you consider those three as one group and also those two are one group. So it's up to you. However, doing this on a base of 5, it's time consuming. I would say it's much smarter if you combine the three of them, because we know where is the CG, the first layer, and we know where is the CG of the second layer, and that's where we are able to find the CG of the entire point group. Okay, so I'm going to show you here. Guys, listen. So here is the centroid of the first layer, same as question number 1. And here is the centroid of the second layer. So what you want to do is simply, you need to multiply the area of the first layer, multiply by where is the centroid from the datum, which is simply cover plus stirrup plus half bar. And then you add to that the area of the second layer, multiply by how far the CG from the same datum. And you will see those number in action here in my math. So 300 times 3 times 500, that's your first layer area. You multiply times cover plus a stirrup plus half bar. And then the second layer, it's 20M. How did I get the 300? Anybody tell me, how do I get the 300? Mahdi, say it.
Back in the chart.
In the chart, yeah, in the same table. 20M has a 300 square millimeter from the table. Thanks. And then you go ahead and multiply this times wherever the CG. So the CG here is kind of far north, right? It's 40 cover plus 10, which is the stirrup, and then plus one whole bar, which is 25M, and whole spacing, and then half of the bar diameter of the second layer. Okay, and then finally you divide by the sum of the areas, which is 325M plus 220M. Then finally you get this D prime, and then here we go, your D is equal to your H minus D prime, and then you're also able to find the rho S, sorry, the rho, which is reinforcement ratio, by dividing the entire area of steel of the main reinforcement. So 325M plus 220M, you divide it by B times D, and then you get here 0.0097, which is 1%, roughly 1%. Now, I also wanted here to bring your attention, which already Brody mentioned, and that's why he got 4 marks. Notice how centroid moves for the 3 solved example. Does it make sense? Looks like it does for Brody. Can I hear, does it make sense for you guys? Can I hear that?
Tahir, is there like a labeled that formula that you just showed? I almost got an aneurysm. Is there like something that labels what is what, so like when I look at it I know exactly what to look for? Yeah, right there.
Okay. So guys, I'm gonna maybe do it here now, so it's in the video, and you wanna take a note. So let me show you. Okay, I'm gonna show you. So let's say I'm gonna, in order for you to find the where is the centroid, you must have a datum, any datum. It doesn't matter what is the datum. You choose any reference line. And let's say, here we go. I have here anything. For example, let's say, sorry guys, be patient, please. So ellipsoid. So I'm gonna draw here something like that, and then another thing like that. Okay. So what happened here is you wanna so I'm gonna maybe do some labeling. So I'm gonna put this one as A1. Please be patient because it takes me some time to draw. And then I'm gonna label this one as A2. Okay, and we want to find where is the centroid. Okay, so the centroid is, you must pick a reference line, and then you go ahead and multiply A1 times Y1. Where is Y1? I'm not sure if I have the, yeah, I have the dimension line here. So the Y1, it goes from the centroid of this area, which is here, it goes to my datum. So this guy is your Y1. Okay. Okay. Next is I need to add to that A2. So dimension line, and then A2 multiplied by the how far from the same datum. So this will be Y2. Okay. Now let's try to apply this equation to this simple problem. So my D prime, I'm gonna write text. My D prime equals A1 times Y1 or Y1 plus A2 times Y2, and then finally divide by A1 plus A2. Okay. I'm not sure if this helps. Does it? I don't hear you. Does it help?
Sorry,
That
I was
helps a
just
lot.
I was talking to myself. I was on mute. Yeah, that looks a lot better.
Okay, so you guys know what to do. It's just like for a centroid calculation, you pick a reference. In our case here, we picked the bottom of our beam, and simply we have to multiply every area times how far the centroid of this area from the reference line, and we do the sum, and then finally we divide by the sum of the areas. So that's how we do it. Okay. Okay, guys, we're very close to finish, and so guys, I'm gonna go here, and then before we end today, I wanna go with you through the behavior of the beam, and I mean the beam in this case will be different from the beam that we will design this year. If we make our beam without any rebar, okay, we simply form our beam, we place no rebar, and simply we bore it. So in this case, our beam will be called non-reinforced beam, a beam without any reinforcement. And in this next 2 slides, I'm going to explain for you how does it behave. So you can see here, I have an elevation. I call it beam elevation, and the beam is assembly supported, not a cantilever, not fixed, because it has to support. You can see them on my elevation. And then I applied a point load in the middle, I'm calling this force F. And then I will increase the force F from zero. I keep increasing, adding more loads. I'm going to show you right now what happens to the beam as you increase the load. Okay, let me ask you before we do that. And by the way, you have to remember this from strength of material. So I'm going to zoom into this side here. And what is this side? What do you see in your screen right now? You see on the left a beam section. So that's a section through the beam. Very simple rectangular section with width B and height H. And simply when I start from 0, and then I keep increasing my F a little bit. So what happens to the moment? The moment will increase. So there will be a bending moment that's trying to bend this beam. And remember, the load is very little. And remember, my beam has no reinforcement, zero reinforcement. It's just plain concrete. Okay? Now, we know that when we apply bending moment to this beam, before it cracks, there is something called the neutral axe. The neutral axe is where we have zero stress and zero strain. Neutral axe is where we have zero stress and zero strain. So what happens is, above the neutral axe will be one type of stress, and on the opposite side from the neutral axe, the stress will change. What does it mean? It means one side will be compression and the other side will be tension. Are you following? Do you approve what I said?
Yes.
Okay, before my beam cracks, where is my centroid? Before it cracks, which means concrete is working in tension and compression. Where is my neutral axe? It's exactly in the middle. And it works exactly like if you have a wood beam or a steel beam, it is the section is working fully in tension and compression. Yes, after the cracking, then there's a different discussion. But now we are before cracking. So simply the neutral axe is in the middle. Now let me ask you, what is the stress distribution on the cross section? So you think all the fibers, they will have the same amount of stress? Do you think all the fibers in my beam, do they have all the same amount of stress, or the stress will vary depending on how far the fiber from the neutral axe? Please tell me, show your hands and tell me. Prodi, go ahead.
It'll vary. So on the top side, most compression. On the bottom, most tension.
Fantastic. Thank you so much. Hopefully the class agree. So the stress along my cross section, and on the right side here, that is my stress diagram. Hopefully Brody got it from last year, not from my screen. Okay. And so you can see here, this is stress diagram, and the fibers will get different stress based on how far the point from the neutral axe. For example, if I have a 1 point here, I'm going to point to my point. If I have 1 point here, which is a distance axe, guess what is the stress? The stresses can be estimated from this equation. So the stresses here, F is equal to moment divided by the moment of inertia multiplied by Y, which is how far from the neutral axe. Okay, and I wrote this here. I said stress, F is a stress at any point at distance Y from the neutral axe in MBA. Okay, and obviously, guys, where is the maximum stress? As Brody said, it will be maximum where Y is equal to H over 2. Okay, so you can see here, obviously, at these fibers, so this fiber here will have maximum tension, and this fiber here will have maximum compression. Hopefully you agree. Okay, now, something on the side is not really connected right now, but how much is my moment? So we're talking about F. How the F is connected to my moment. This is something from first year statics. If you have a single point or point load that acts in the middle of your beam, then in this case your moment is equal to F multiplied by L divided by 4. Okay, not WL squared over 8. WL squared over 8 only when you have a uniform load. But if you have a point load that the value is F, then the moment is equal to F multiplied by L divided by 4, and the assumption here is in the middle. And I will change my slide because this one is not general. If the load is not in the middle, then it's a different equation. I will change that for you. I'm sorry for that. Okay, I'll take a note. Okay, now next is what is I in this equation? Do you guys remember what is I? I is the moment of inertia, or sometimes called second moment of area. So it depends on where you study. Sometimes call it moment of inertia, and in other literature they call it second moment of area. So for a rectangular cross section, this is something you're supposed to know from last year. Is the width of your beam multiplied by the height of your beam or the depth of your beam cube divided by 12. That's for any rectangular section. The moment of inertia. And by the way, the units are in millimeter to the power 4. And that's how we find the stress. So guys, let me ask you, okay, I'm going to go back to here, forget about math. And why do you see 3 different colors on my stress diagram, like cyan, and then followed by green, and then finally followed by red? And by the way, the colors are on purpose. The colors are on purpose, okay? So what happens here, as I increase, if I have zero load, no load, it means I have no stress in my beam. When I increase my load more, I will get the cyan. When I increase my force F, the moment will increase, and I will get the green until one point where the moment will go to the maximum moment that this beam can take, and we are at the red. Okay, at the red. So when do we get the red? What signifies the red? What characterizes the red? Simply, if the stress, and please say if what I'm going to say makes sense for you or no. When the stress at the bottom fiber here, this amount of stress is equal to F sub R. And what is F sub R? If you learned something today, what is F sub R? What is F sub R? Did you learn today F sub R, which is called, any help?
The modulus of rupture or
Is
rupture.
that Nico?
Yeah.
Thank you, sir. Couple of marks for you, Nico. That's true. And what is the modulus of rupture in plain English? It means how much concrete can take in tension. Concrete is fantastic in compression and will never fail here. Okay? will never fail here because it's weaker in tension. So as soon as the stress at the bottom fibers will become equal to F sub R, which is, for example, 3 MPa or 2 MPa, it depends on FC dash, then here we go. So this is where the beam will fail. This math is available here. So the beam will crack at the tension side when F, which is a stress, is equal to F sub R, which we can estimate this through the equation 0.6 times lambda, which is 1, multiplied by F square root of FC dash. So which means, guys, from this discussion here, we are able to mathematically find what is the value of the moment that can simply crack my beam. Look at this, please. So I'll go back to here. We know few things. Number one, we know that if this value equal to F sub R, my beam will fail. And we know also if this value is maximum, which is H over 2, this is the fiber that has the highest tension. So very simple. All you have to do is, in this equation here, you put the F equal to F sub R, like 3 MPa. You put here in this equation here, the Y equal to H over 2, the height of the beam divided by 2, where you have the highest stress. Then what you get is the moment that cracks your beam. And that's what's happening here. I just used the math, and MCR, which is cracking moment, is equal to F sub R multiplied by I divided by H over 2, which is the maximum Y to the at extreme fibers. Okay, guys, we're going to do this in numbers next class. We have 4 minutes. We'll just ask you for questions. Key questions. Okay, so looks like sleepy. No questions. Okay, anyway, you have the slides, please. Again, I'm gonna say I'm not gonna give up on this advice for you. If you want to make your life easy, you just have to study whatever we learned today. It's going to take you this much now or today, but if you try to study the same thing again in a week or two, then good luck with that. It will take you forever. Things are fresh right now. You just heard me. The best is if you are able to do it today or maybe tomorrow. I know there is a medical fact within 72 hours. The information is somewhere here in your brain, and after 72 hours, it goes somewhere else. So please do that before 72 hours. Guys, if you have no question, then you know what to do, huh? Enjoy the rest of your day. Thank you. Thank you, guys.